Let's go over an example. Okay, so in this case, you basically have, and I'm drawing the crack like a square. It's just easy to understand or easy to see where the crack is. So you basically have an edge crack, in this case more like two plates bonded together or somehow fused together. So the load was applied to, for example, to fix the bottom and the top surface, but move both basically horizontally down by a distance of V0. So this is the kind of you, for example, you weld a very thick plate on the top and the surface, and then you, on that plate you have a hook. You're trying to hook it up and open the crack up. So I have, just to make things easy, the thickness is the same on the top and the bottom section, and then my X will be set up just like regular. So in this case, what I'm going to choose is I want to go counterclockwise, right? And we said that's commonly what we do. So we can start with the edge. Why do I start at this point? Or do you have a better choice?
I think the stresses are too.
Right. So I will choose, in this case, I choose A because I want to go down, or I put A prime. A, because I want to take advantage of this surface. What's so special about that surface? Because the stress, the traction forces are zero, right? And so once I decide that, I'm going to go along this to point B on the other side, and then I go up C over here. So that, again, is BC because the traction forces are zero. So that's what I want to take advantage of. So if you're looking at a J integral, take advantage of the free surfaces because those are the ones that make your calculation much easier, and then D and then D prime. So I come up, I go horizontal, I come down, and I end up at D prime. So that's my path for my J integral calculation. So in this case, they want me to find J and K1. And I didn't mention that. I mentioned it over here. So for a linear elastic, my J integral is equal to my strain energy release rate, and that, of course, is equal to K1 over E prime. Was it prime from square or E prime? K1 square over E. Okay, so if you know J, you can calculate the K1 as long as you know your E. So let's do the J integral. So we know our J integral is equal to You just write down the path is A prime to A plus A to B plus B to C plus C to D and plus A prime to D or D to A prime. D to D prime. Okay. And also you'll notice this is symmetric, right? So what that means is A prime A is going to be D equal to D prime. And that is going to be equal to that. So I can reduce that to So that's what I have. So I really only need to worry about these three sections. So let's look at, and just to make things easier, that we copy down what is the J integral over here. So my J integral is so that's the equation I'm going to use. Okay, so let's look at section A prime and the A. So in this case, let's look at the first term over here. So we had that dy. Last time we had the dy equal to 0. In this case, do I have dy equal to 0? No, right? My dy is not equal to 0. So that means I need to calculate my w. So my w is 1 over 2 sigma ij epsilon ij. And so that's all the stress components I have. In here, what stress components do I have along A prime and the A? Along the surface. Yeah, all 0? So let's see. We have sigma ij is equal to sigma xx, sigma yy, and tau xy. Right? From the attraction-free boundary condition, we know sigma xx is equal to 0, that is equal to 0. Right? Do we know sigma yy? In this case, we don't know that. But do we know epsilon yy? So what's the definition of epsilon yy?
Elongation.
Epsilon yy is elongation?
The strength.
It's a strain, right? So what's the equation for the strain? If I have my displacements in U and the B, will be dV over dy, right? So in this case, so that means it's the change of rate of my displacement along the y direction over that y direction, right? So what would be that term? Do we know that term?
It was beyond
get some money.
So there is two displacement like B naught.
Right, so I have a displacement V naught that is coming down. So what this look at is, if I have two locations over here, y1 and the y2, right? So you can think of this into v y1 minus v y2 over y1 minus y2. Right? In the extreme case, that if we don't know this, but that numerical integration would be like this. Okay? So basically, I'm looking at 2 points around the surface and to see if they come down or if they deform along the y direction in the same way. In this case, do we know these two terms? So assume this, they didn't give the length of the crack, so that means the crack will be long enough. So when you have crack long enough, and then you limit that movement to be straight down, what does that mean is this edge, if it's far away from the crack tip, it's going to just come down.
No relative displacement between.
Right. So you essentially have only rigid body motion. You don't have deformation. Does it make sense? Right? So in that case, if you have just rigid body motion with no displacement or with no relative displacement, then this will be equal to, let me move over here. So that equal to 0 because of rigid body motion. Okay. So now, because of epsilon y is 0, then that means sigma y will be 0 as well. So the first term will be 0, so I don't need to worry about that. The second term, of course, in this case, what is T1? T1, this time should be easy.
Now it should be 0. Tau x, y,
Should be, is a T1 in this case is tau xy? T1 is a traction force along x. So that will be,
Sigma y fraction force.
why is sigma y along x?
Like this.
So that will be sigma xx times dy, right? And then that of course is equal to 0. My T2 is tau xy times dy. And that is equal to 0. So basically all of those,
Sigma xx is unknown. Why can we say?
sigma xx is unknown. So you have a surface over here, right? So this is A prime A I'm talking about. So your traction force is sigma xx and tau xy, right? And you have a free surface. So this is something that sounds easy enough, but a lot of students messed up. So just if you're not sure, draw the surface and then draw the normal and the shear stress components. And if it's free, those two components goes to 0. So if you, of course, that's x and the y is 0. Okay. So from here you get the second term is all 0. So by combining these two, you get j of A prime A is the same as j of D prime is equal to 0. Okay, so that's for the first section. So let's look at the section AB. Okay, For section AB, so just to prevent confusion, I'm going to draw this over here. And my x is horizontal, my y is perpendicular. So now I go back to here again. So now I have a horizontal line, so that means my dy is equal to 0. Right? So I don't need to worry about the first one at all. Now, so the second one is what I'm worried about. So we have, in this case, so now with that, I have integral of over AB. First term goes to 0. The second one is my T1. So I will call the Tx dux over dx minus Ty dy over dx times ds is the same as dx. Okay, so in this case, do I know my Tx or Ty?
Tx 0.
Tx will be, what will be my Tx in this case? Is a tau xy. It might be 0, but I'm not sure. Could be. Okay, so my Ty will be my sigma yy. Do I know my sigma yy? But I'm not sure, because we have a deformation for sure, right? And on this side, we said that my sigma yy is 0 because there's a free end. But when I come to here, my sigma yy is connected to the other side that is constrained. So that most likely I will not have 0 over there, right? Okay, so move on. So if it's not 0, that's not worry about for now. No, actually, well, let's see. Okay. Do we know this guy? It should be 0, right? So this is the deformation along the x direction, most likely, and the rate of change along. So dux over dx should be equal to 0. Okay? So we don't need to worry about tx in this case. Okay. Do we know about this guy? It also should be 0, right? So this is the change of the displacement along y, which is coming down, and then the change of that along x direction. So if I come down like this, I don't have any change of along x. So my dy over dx also equal to 0. Mm-hmm.
In the first case, what about the Poisson's distribution for the del ux by del x?
Which one? For A prime A or
No,
for this
the
one?
same section.
For this one? For section AB, this guy?
No, del ux by del x is 0.
This one?
Yes.
Okay.
What about the Poisson's distribution? There will be some displacement in the next direction.
Okay. So you're thinking of that the dux going in this direction? Right, the question is what they change along the x direction. Right? Or one way to think of is if you draw basically a grid. So if I have, let me just draw the lower part. And if I have, say, grid lines on this body, right? And then if I move, like I bond this to a very thick plate, and I add a load on that. Will that grid line change? How would that grid line change?
Not changes along with
It's getting elongated. So what you're thinking is that because of Poisson ratio, it needs to be contract on this way. And so you will see something goes like that. But that in fact probably is very small. So in this case, you just consider it's coming down instead of in the lateral direction. Yeah. That's a good question. Okay, so in this case, I have dux and the dy all equal to 0. So I really don't need to care about whether tx and ty equal to 0 or not. Right? So this is for something, if you run into this problem, don't beat yourself up to say, I need to find the tx and ty. Look at the four components and to see if you can set something to 0. Because if you set 1 equal to 0, you don't need to worry about the other components. Okay, so now I start to get worried, and now I have checked those two, they're all 0. So from here we get j of kb is equal to 0. And that, of course, the CD is the same way because of symmetry. Yeah. Okay, so now you know that BC has to not equal to 0, right? If BC equal to 0, then we got 0. Clearly, that's not right. So now let's find the BC. Okay, so BC, I draw it over here. So the traction force, again, will be Tx and the Ty over here. So we go back to that equation over here. First of all, I look at the first term. My dy is not 0. So that means I need to find my w, right? And then my w is related to the 3 stress components. So I have dy is not equal to 0, so I need to find my sigma ij is equal to xx y. Okay, so in this case, which components is known to 0, and which one could be found out?
Sigma xx 0.
Sigma xx is 0, right? So that's the to 0. Tau xy is 0. And because of that, that means from here we can get my tx is equal to 0, and my ty is equal to 0. So my sigma y definitely will not be equal to 0, because from here my second term is already gone, right? And all the others, so sigma y definitely for sure is not 0, otherwise it will be equal to 0. So what would be my sigma y in this case? And you can look at this problem the problem is given there's no force conditions, right? It didn't give you any external force information. The only information I gave you is that information. So that means you will not be able to find the stress from equation of equilibrium. The only way you're finding the stress is from displacement, right? So
Strain times
the Young's modulus. So now the question is, what will be my strain over here? Because now I can relate to the strain to my displacement, and then I solve the problem.
So the strain can be changed in the displacement that would be 2
Right.
times V naught.
Exactly. So I have E. So my epsilon y would be change of distance will be V naught over original length is 2h. Right? So that will be. Okay. So from that, of course, my W is 1/2. And all the other components is 0, so I only have sigma yy, epsilon yy over here. So I plug that in, so that E over 2, squared. Okay, so I plug into that, so my J integral is equal to gamma, so now I know over dy, so that's minus h, 2h of E over 2. And so you plug your numbers, you get E over 2. Let's cancel out. Good. Okay, so in this case, really I should use the effective add a prime to the Young's modulus, so that covers both plane strain and plane stress. Okay, so from here, of course, that's easy. So now I know that my J integral is just contributed by the section BC, and it's going to be equal to E prime V0 squared over H. And then, of course, from here, I can calculate my K1 is equal to square root of that give me Okay, so that's how you calculate the J integral. Basically, what you need really just be a little bit meticulous about it. So this is the equation you will use, and make sure you check each component to make sure you don't miss any component that is not supposed to be 0, and then you set it to 0. And then if you have really trouble solving it, it most likely is that there's a component that's supposed to be 0 that you didn't think of it's to be 0. So when you solve the problem, the trick is look at each component, check whether they are 0 or not, or whether you can solve it. So it's relatively straightforward. Okay. So of course, once you have this, as I said, for nearly elastic material, the J integral is related to your K1C. So you can see that the propagation criterion applies. So this also applies to nonlinear elastic material. So in this case, for nonlinear elastic material, you basically have a J integral fracture criterion. And that, again, as I said, the engineers are really boring. So they come up a critical J integral, and then that if it goes above that critical threshold, then your crab will propagate.